Hi, this is Mario Sioutis, and today I will introduce our efforts towards an open source web API implementation for ECHONET Lite. The contents of this presentation are as follows, and I hope you enjoy the talk. As a brief introduction, the ECHONET Lite ecosystem consists mostly of devices and specialized applications called controllers. In recent years, the Web API Gateway concept has been introduced, and we will see why it is necessary in a moment. In order to improve its value proposition and gain in user popularity, the ECHONET Lite protocol must overcome its current limitations. It is a local area network protocol that utilizes a binary data format. To attract more users, it should provide access from anywhere and make its users easier. This can be achieved by providing a Web API. This allows the reuse of countless pre-existing user and developer applications and also simplifies the development of new applications. The ECHONET Lite Web API guidelines were first released in 2018 and define a Web API for interaction with ECHONET Lite devices and controllers. These guidelines focus on the client side and provide a set of device descriptions which specify the data format through JSON schemas. Furthermore, the guidelines describe various API endpoints that can be used for setting and getting a property, as well as receiving notifications. It is important to note that, at this moment, the implementation of the Web API guidelines as a web server is considered an implementation detail. For research purposes, we pursued an open-source Web API implementation of the guidelines. This implementation is a two-part solution consisting of a front-end and a back-end. It is usable right now and covers the most important APIs defined in the guidelines. Development is still ongoing. The source code is released under a 2-clause BSD license and it can be found on GitHub. Our implementations consist of a front-end and a back-end. The front-end of the system is a web service that is responsible for communicating with web clients. This front-end is suitable for deployment in the cloud. The backend of the system consists of a specialized home controller application, which is typically deployed in the home network and communicates with devices using the ECHONET Lite protocol. These two parts of the system exchange information using a simple, text-based, line-oriented protocol over TCP/IP sockets. Moving on to the front end, its project name is Weblite. It is developed using the Rust programming language and utilizes two key technologies. First, the Actix web framework, and Serde, a framework for serializing and deserializing Rust data structures. The frontend is based on version 1.0 of the guidelines and supports the APIs listed. Briefly, it can list up the devices available in the network and allows setting and getting of their properties with appropriate error handling. We have plans to support notifications using WebSockets. Over the next few minutes, we will demonstrate the use and the various properties of the frontend. Some sensitive details have been blurred out, and all time measurements have been taken using the time Unix utility. First, the frontend has a startup time of roughly 5 seconds. During this time, it parses all available device descriptions and also performs device discovery. The information gathered includes lists of the properties its device has, as well as information regarding the ECHONET Lite protocol version, appendix version, and manufacturer code. Using the Properties API endpoint, we are able to list all the properties of a device. Here are the properties of a device with class of general lighting that is present in our experiment environment. The request concludes in 300 milliseconds. The Device ID API endpoint provides the client with information about a device, such as its type and a description. Furthermore, information about properties and their data schema is also presented. This information is generated for each device instance that was discovered, and it contains only information that is both defined in the device descriptions and also present on the device itself. This includes common items that are present in the ECHONET Lite object superclass. The Devices API endpoint is useful for listing the devices that are available for use. For each device, the supported ECHONET Lite protocol version, its appendix version, as well as manufacturer information is present if it exists. In order to adhere to the guidelines, some of the information needs to be presented in human-readable format instead of binary representation. This will be addressed in future releases. Here, we demonstrate the error handling functionality of the front end. A 404 resource not found error will be generated in case of a misspelled device or property name. If the user makes a request that does not follow the schema, a 400 bad request error will be generated, pointing to the erroneous data whenever this is possible. Finally, the following segment demonstrates the use of the property API endpoint, as well as showing actual usage of the front end using command line tools. Please enjoy. Let us now move on to the backend. Its project name is Ecology, and it is used as an ECHONET Lite command proxy and source of notifications. It is written in Java, and it utilizes Protolite, an ECHONET Lite library we've developed and maintained since 2012. It makes heavy use of threads in order to avoid any serial processing bottlenecks. The communication protocol between the frontend and the backend is a text-based, line-oriented protocol running over TCP/IP. For a request, a target must be specified, with optional data in the case of a set command. A response contains a simple OK and an NG field, indicating success and failure respectively. It further contains the responder, as well as any data in the case of a GET command. Targets and responders follow the same format, which consists of an IP address, the ECHONET object, and the ECHONET property code, all separated by colons. Using this protocol, the backend can provide interactive sessions using, for example, Telnet and Netcat. It supports multicast address and all object instance queries, as well as support for requests that span multiple lines. It is easier to understand the wire protocol using an example. Here, we attempt to retrieve the temperature of all temperature sensors present in the network. We use a special multicast address for ECHONET nodes, then specify the temperature sensor object with instance code 0, and finally the property code. Since no set data is present, this request is a GET request. The responses come in with the result of OK, responder information, and the temperature data as binary information. In this example, we're using Telnet to turn off a light. After specifying the target, we append a comma and the set data that correspond to setting the operation status to off. The request was successful and no property data is present in the response. Finally, the backend is capable of providing a live stream of notifications that are multicast throughout the ECHONET Lite network. The first field is marked with the initials INF, then comes the notification source formatted as a target, and finally the binary data. This notification stream is available through a different port. In this section, we will explain in greater detail some of our implementation choices and express our thoughts about certain aspects of the Web API guidelines. Let's have a look at the initialization sequence first. The frontend starts by parsing all available device descriptions. Then, using a multicast query, it asks all nodes for the device classes that they implement. After that, the intersection of all classes that have device descriptions and are present on the network is determined. For all instances of these classes, their properties are gathered, and with this information, customized device descriptions are generated. These device descriptions include common items and exclude properties that were not present in the actual device. Finally, information regarding the protocol and appendix version, as well as manufacturer information, is collected, and then the front end becomes ready to accept client requests. A large part of the front end's work consists of converting data. The front end is responsible for converting data from JSON requests to binary ECHONET Lite data and vice versa. Unfortunately, in most cases, the device descriptions are not sufficient for this task. Our proposed approach consists of A, using the device descriptions in the cases where they provide enough information, and B, supplement them with additional information whenever necessary. For example, an object schema may require specific properties to be present, as well as their ordering. For numbers, we may need to supplement minimum and maximum values, and for enums, we may need to supply the actual APC values. In my personal opinion, this is the single biggest aspect of the guidelines that is lacking. With a large number of ECHONET Lite devices and properties, implementation becomes very difficult. We believe that the data conversion problem is within the scope of the guidelines and that should be addressed if we expect more implementations that are interoperable and correct to materialize. Here are a few notes regarding the device descriptions. In release version 1.1.1, only 27 out of 43 device descriptions were error-free, but after patching them, this number increased to 39. However, no sensor device descriptions are present. This situation improved with version 1.2, and we also now participate on the relevant working group reporting our findings. My impression is that device descriptions have too many optional features right now, and that they should be more restrained. Our efforts resulted in a few more contributions. Most notably, we developed a device description parser called DDCheck, which helps identify errors present in device descriptions. Furthermore, we developed 6 device descriptions that target sensors. We developed device descriptions for temperature sensors, humidity sensors, illumination sensors, VOC and CO2 sensors, as well as human presence detection sensors. Moving on to our experiment section, we start off with our experiment setup. Our most important goal was to understand the amount of time overhead that the introduction of the web service induces. To this end, we designed 2 paths. The first one involving a generic HTTP client and the front end, whereas in the second path we deployed a specialized application that communicates directly with the backend. In both paths, the backend and the devices used were the same. In terms of networking, the HTTP client, the web frontend, and the specialized application were run on the same home computer, which in turn connects over a VPN tunnel with the backend. And here are the results. In the first scenario, a single device property was accessed 100 times and the results were recorded. The web API path, path 1, turned out to be on average 200 milliseconds slower compared to path 2. This overhead is very similar to when a client request results in an error that's handled locally. In the second scenario, we compare execution time when making 1 and 2 concurrent requests. The execution time did not increase, showing that the system is perfectly capable of handling requests at the same time and that the workload is parallelizable. When it comes to memory consumption, we did not observe anything out of the ordinary. The front end is running a debug build of the program, and it consumed roughly 12 megabytes. In contrast, the backend consumed 75 megabytes, something that is completely normal considering that it is a Java application. In summary, we believe that the Web API will help ECHONET Lite scale beyond the local network. We have provided an open-source Web API implementation that consists of 2 parts. Experiments showed that the implementation exhibits reasonable performance and memory footprint. We want to highlight the JSON to binary conversion problem, and we believe that it should be addressed by the guidelines. Finally, we also contributed a device description parser, as well as some sensor device descriptions. I hope that you have found this presentation to be interesting. Thank you for your time.